Hello everyone, this is Mr. V. Hill. Today we're going to be talking about linear programming. And we're just going to work through an example. You're going to want to watch this several times. I doubt you're going to catch everything the first time through. But the point of linear programming is to optimize what's called an objective function here. So here's our objective function, p equals 6 times x plus 7 times y. You could use any letter you want for this third variable. Notice we have two variables here. The third one here is the dependent variable. It is dependent on these two independent variables. We're going to talk about this more in class and what the actual visual representation of this is. But for right now, just notice that every pair x and y is going to give us some unique p value. So this is a function. You can't get two different p's for the same x and y. Okay. So this is a function of two independent variables. We could call this z, could call this f of the ordered pair x, y, lots of different notations here. But this is what we call the objective function. We want to find the maximum value of this. This might be something like profit, or we might want to minimize costs. Either way, we want to optimize it, meaning we either find the maximum value of this p or the minimum value of this p. Now we can't do that unless we restrict what x and y have to be. So we're going to maximize this function given these constraints that we have written right here. Notice this is a system of 4 inequalities. And now these are all linear inequalities, and this is a linear function of two variables, hence the name linear programming. If these things aren't linear, this is all going to fall apart and not work. But the way we're going to do this is we're going to first graph the system of inequalities, which are our constraints. So these first two are just saying that x and y have to be non-negative, greater than or equal to 0. All that really means is that we're operating in the first quadrant. So I'm not going to color these ones in just because it's going to clutter up our graph over here. Just understand that, of course, we can't be left of the y-axis or below the x-axis. Okay? That's all these two first inequalities are telling us. Now, we can graph these second two just like we know how to do. Well, these are both in slope-intercept form, except that they're inequalities, so we can graph them quite easily. If I go by a scale of 2 here I have a y-intercept of 10. I put that right here. 2, 4, 6, 8, 10. Then I follow my slope of negative 5/6. So go down 2, 4, 5, and then run to the right 2, 4, 6. Here is a second point. And I could just play connect the dots here, or I could follow, go down 5 again, and to the right another 6. Here's a third point. So this inequality, the boundary line, which I do want to include, so I'm going to use a solid line, is going to be right here. And since I want the y's to be less than or equal to this expression, smaller y's are down, so I'm going to shade down this way. I won't go below the x-axis because I also know that the y's have to be bigger than 0. So it's this area right here. The last inequality, we can do that again. So here we have a y-intercept of 15. 2, 4, 6, 8, 10, 12, 14, 15. There is our y-intercept for the boundary line. And then we need to go and follow our slope of negative 5/3. So down 5 to the right 3, down another 5 to the right 3. Oh, hey, that's nice. I think we're landing on that point right there. Down another 5 to the right 3. There we go. And so we want to include that boundary line since it's less than or equal to. And then we're going to shade below this line again because this y is less than or equal to. So we're shading everything below this line. And so the whole system of inequalities is going to be to the right of the y-axis, above the x-axis, below this section of the line right here, and below this section of this other line right here. So it's all of this stuff in this quadrilateral. Okay. So these four inequalities give us the four sides of the quadrilateral. That's not always going to be the case, but we're going to usually get some form of polygon. Might be an open region, but we'll see some more examples in class. But this thing right here, this is what we call the feasible region. And that's just the name we give to the graph of this system of inequalities, which we call the constraints. Okay. So the big idea here is that every single point x, y in this feasible region will spit out a value for p. Okay. Now, the interesting thing is, since all of these functions are linear, and specifically this objective function is linear, what we're going to see, and then we'll talk about this more in class, we kind of need to visualize this in a three-dimensional way, which is very difficult to do on this video. But the big point here is that the maximum and minimum values of this objective function for this feasible region have to occur at the vertices. Those are the only ones that we are concerned with. Okay? So this vertex up here is the point 0, 10. Of course, we have this point down here at 0, 0. If we solve for the x-intercept in this last equation, what we're going to see is this thing is going to be the point 8, 0. I'll write that a little bit more visibly. And then this point right here is the point 6, 5, which if we just graph that very carefully, we should be able to see that no problem. Sometimes it won't be so obvious, in which case we might need to solve the system of equations that come out when we just consider, instead of less than or equal to and less than or equal to here, we just replace these with equal signs. Of course, and that'll give us the boundary lines. The solution to that system of equations would be the intersection point right there. So we might see some of these vertices right away from the graph, or we might have to do a little bit more work. But the big point here is, since this objective function is linear, the maximum value and the minimum value, either way one we're looking for, has to occur at one of the vertices. So all we have to do to figure out what the maximum value is just figure out what the value of p is at each of these vertices. Okay? Meaning we plug in this x and this y, see what p is. Take this one, take this and this x and this y, plug it in here, see what p is. And we just pick the biggest one. That one has to be the actual maximum value. Okay? So let's check these out. P of 0, 0, meaning the p-value that we get when the x is 0 and the y is 0, well, that's just going to be what we get when we plug it in. 6 times 0 plus 7 times 0, that's of course 0. Okay. That's for that vertex. Let's check this one, 0, 10. P of 0, 10, well, that's going to be 6 times 0 plus 7 times 10, which is, of course, well, that's 0. This is 70, so it's 70. Okay. Let's check this vertex down here. P of 8, 0. Well, we go 6 times 8 plus 7 times 0. Well, 6 times 8 is, of course, 48, plus 7 times 0 is 0. And so finally we check this point 6,5. And that's going to be 6 times 6 plus 7 times 5. 6 times 6 is 36. 7 times 5 is 35. So this is going to be 71. And so that is our maximum value. It's the biggest of these p's. That has to be the maximum. So the maximum of p equals 71 occurs at the point 6, 5. So when x is 6 and y is 5, we get the maximum value of p being 71. Okay? So that's how we apply linear programming. Now we're going to need to see this in some context, see how it works in so-called real-life situations, but that's the basic idea. You're given a function that you want to optimize. You either want to find the maximum value or the minimum value. It'll still work either way. We're going to be given a set of constraints. These constraints are going to give us a feasible region. We find the feasible region just by graphing the constraints. Once we've graphed that feasible region, we figure out what the vertices of the feasible region are, and we check and see what the value of the objective function is at each of those vertices. The biggest one will be the maximum value, the smallest one will be the minimum value. So the minimum value of p for this particular feasible region is 0, the maximum is 71, and that maximum of 71 occurs at 6, 5. Okay. You might want to watch that again to make sure you caught everything. Because now, what I want you to do is this practice problem. Maximize this function. It's very similar to the one we just saw, given these constraints. Now you've only got 3 of them. Have that ready for next class. Thanks for watching.